In 1889, the World's Columbian Exposition began construction in Chicago. The official timeline states that over 200 buildings covering 690 acres were designed, built, and finished in under 3 years. Most were demolished by 1894. But here's the friction. The Palace of Fine Arts alone required 120,000 square feet of interior exhibition space, with structural loads calculated for marble sculptures weighing several tons each. The machinery hall spanned 842 feet without interior columns. Contemporary construction records from similar civic projects show timelines of 6 to 8 years for buildings 1/10 the size. The Paris Exposition of 1889 faced similar mathematics. The Eiffel Tower took 2 years with 300 workers. The Galerie des Machines took 18 months. The Chicago Fair had 47 buildings of comparable engineering complexity, built simultaneously in roughly the same time frame. Whether this represents forgotten construction methods or compressed official records. Let me be direct about what this script examines. We're looking at architectural documentation, infrastructure timelines, and demographic patterns from the mid-1800s that don't align cleanly with accepted historical narratives. This isn't about proving conspiracy. It's about observing friction in the timeline and asking what generates it. Some call this the Tartaria question. We're simply following the architectural evidence. The standard explanation holds that rapid industrialization, combined with temporary building methods using staff and plaster, allowed unprecedented construction speed. Most exposition buildings weren't meant to last. They were theatrical facades on wooden frames. But that explanation bends when you examine the engineering specifications. The 1893 agricultural building had a floor area of 500,000 square feet. Its central dome rose 212 feet. The structural drawings show steel framework with concrete and iron cladding. The manufacturer's building covered 31 acres under a single roof, the largest enclosed space in the world at that time. Its steel arches weighed 2,400 tons. These weren't movie sets. In 1915, San Francisco hosted the Panama Pacific International Exposition. 11 palaces built in under 2 years. The Palace of Fine Arts featured a 162-foot rotunda with coffered dome and classical colonnade. Today, it's one of the few structures that survived, because it was rebuilt in the 1960s using modern concrete. The original was described as temporary construction. If it was temporary, why does the 1915 structural documentation specify steel reinforcement, foundation pilings, and load-bearing calculations identical to permanent civic architecture? Philadelphia's Centennial Exposition of 1876 presents similar numbers. Memorial Hall, 365 feet long, 210 feet wide, central dome 150 feet high. Construction time 18 months. The building still stands. Its granite and glass construction required quarrying, rail transport, and precision stonework. The official timeline suggests 40 to 60 workers completed it faster than modern projects with hydraulic equipment and computer-aided design. Machinery Hall at the same exposition covered 21 acres. It housed the Corliss steam engine, a 1,400 horsepower machine weighing 680 tons. The hall's floor required reinforcement to support distributed industrial equipment totaling over 3,000 tons. The math doesn't reconcile with pre-industrial labor capacity. Here's where the pattern thickens. These weren't isolated events. Between 1851 and 1915, over 40 major World's Fairs occurred across Europe and North America. Each featured monumental architecture built on compressed timelines. Each was largely demolished within months of closing. London's Crystal Palace in 1851 covered 990,000 square feet. It was disassembled and rebuilt in a different location by 1854, a process that revealed prefabrication precision uncommon for the era. The building used 293,655 panes of glass. The official record states construction took 9 months. But the Crystal Palace was made of iron and glass, Industrial materials. It's explainable. What's harder to explain is the consistency of architectural style across continents. The 1900 Paris Exposition, the 1893 Chicago Fair, the 1901 Buffalo Pan American, all featured nearly identical Beaux-Arts classical design. Domes, colonnades, symmetrical facades, ornamental detail that required skilled stonemasons. Why would temporary exhibitions demand such uniformity? The timing raises questions about labor allocation. In 1890, Chicago's population was just over 1 million. Constructing the Columbian Exposition required an estimated 10,000 to 15,000 workers at peak. That's 1.5% of the city's total population engaged in a single construction project, while the city simultaneously expanded residential neighborhoods, commercial districts, and infrastructure. Census data from 1890 shows Chicago added 600,000 residents in the previous decade. That means housing construction, water systems, and street grading for hundreds of thousands, concurrent with fair preparation. The same demographic pressure appears in other exposition cities. Paris in 1900, St. Louis in 1904, San Francisco in 1915, each experienced major urban growth during the exact years of fair construction. There's no record of labor shortages, no delays, no strikes due to overextension. The structures themselves show another inconsistency. Many photographs from these fairs depict buildings with weathering patterns, stone discoloration, settled facades, details that suggest age beyond 2 or 3 years. In some images, the fairground buildings appear newer than the surrounding urban construction, but in others they look oddly worn, as if they'd been standing longer than the exposition timeline allows. And then there's the question of demolition. After the Chicago Fair closed in 1893, demolition contracts were issued almost immediately. Most buildings were gone by spring 1894. The same pattern repeats: Paris 1900, Buffalo 1901, St. Louis 1904. Massive structures dismantled in months. Why the urgency? If these were valuable materials, steel, glass, stone, why not repurpose them more gradually? Some were kept. The Palace of Fine Arts in San Francisco, Memorial Hall in Philadelphia, the Museum of Science and Industry in Chicago, formerly the Palace of Fine Arts from 1893. The ones that survived required extensive restoration within decades, despite being built with temporary methods that somehow produced century-lasting foundations. The architectural evidence creates friction against the official timeline. Not proof of anything beyond the timeline itself, just mathematics that feel compressed. And across every exposition, one design constant appears: classical symmetry echoing older European architectural languages, as if the pattern becomes more visible when you look at infrastructure built during the same period, not for exhibitions but for permanence. The Erie Canal opened in 1825. It ran 363 miles from Albany to Buffalo, connecting the Hudson River to the Great Lakes. The official construction timeline, 8 years. But the engineering required 83 locks, 18 aqueducts, and the removal of millions of cubic yards of earth, using hand tools, horses, and black powder. Contemporary European canal projects of similar scope took 15 to 20 years with more advanced equipment. The Erie Canal's infrastructure tells another story. The stone aqueducts show precision masonry that modern restoration teams describe as superior to 19th century standard practice. The lock chambers used interlocking stone blocks cut to tolerances of less than ½ an inch. This level of accuracy typically required experienced guilds and years of apprenticeship. Yet the canal's workforce consisted largely of immigrant laborers with no prior engineering training. The Croton Aqueduct in New York, completed in 1842, brought water 41 miles from Westchester County to Manhattan. It included a masonry dam, underground conduits, and the High Bridge, a stone arch viaduct rising 140 feet above the Harlem River. Construction time, 6 years. The Roman aqueducts, often cited as comparable engineering, took decades and utilized empire-wide resources. The Croton system was built by a city of 300,000 people during an economic depression. Railroad expansion follows similar mathematics. Between 1850 and 1890, the United States laid over 160,000 miles of track. That's an average of 11 miles per day, every day for 40 years, including Sundays, winters, and mountain passes. The first transcontinental railroad, completed in 1869, covered 1,912 miles in 6 years. The work included tunneling through the Sierra Nevada, bridging canyons, and grading cuts through granite. Two companies worked from opposite ends: Union Pacific from the east, Central Pacific from the west. They met at Promontory Summit, Utah, with track alignment precise enough that rails connected without adjustment. No GPS, no laser surveying. Just theodolites and hand calculation across mountain ranges and deserts. The bridges built during this period show engineering that surpasses the expected capability of the era. The Eads Bridge in St. Louis, completed in 1874, used steel arch construction and pneumatic caissons sunk 100 feet below the Mississippi riverbed. Workers experienced decompression sickness, caisson disease, which wasn't medically understood at the time. Yet the project proceeded with mathematical confidence. The arches were designed using cantilever methods that wouldn't become standard practice until the 20th century. The Brooklyn Bridge, finished in 1883, required caissons sunk even deeper, 78 feet on the Brooklyn side, 44 feet on the Manhattan side. The chief engineer, Washington Roebling, became partially paralyzed from caisson disease. He supervised the final years of construction from his apartment, watching through a telescope. The bridge's suspension system used steel cables with load calculations accurate to modern standards. It carried 4 times its design capacity when tested. How did 19th century engineers predict material behavior with such precision? The answer usually given: they overbuilt everything. When uncertain, they added material. But the structures don't show excess, they show optimization. The Eads Bridge used exactly enough steel. The Brooklyn Bridge's cable diameter matches modern recalculation within 2%. This implies either remarkable intuition or access to empirical data that shouldn't exist yet. Storage infrastructure presents another anomaly. The grain elevators of Buffalo, New York, built starting in the 1840s, used vertical storage methods that anticipated 20th century industrial architecture. They were massive concrete silos, some over 100 feet tall, using continuous pour techniques that weren't officially developed until decades later. By 1900, Buffalo had the largest grain storage capacity in the world. Over 40 million bushels. The elevators used conveyor systems, automated weighing, and mechanical sorting that made the city a global shipping hub. Who designed systems that efficient for a city of 350,000 people? The same question applies to urban water systems. Boston's Cochituate Aqueduct, finished in 1848, included the Brookline Reservoir, a holding capacity of 660 million gallons. The distribution network used iron pipes with pressure regulation and valve systems. The entire infrastructure was designed to serve a city of 1 million. Boston's population in 1850, 136,000. Philadelphia's Fairmount Water Works, completed in 1815, pumped water uphill using steam engines and delivered it through a distribution grid covering the entire city. It included decorative neoclassical buildings that doubled as functional pump houses, architecture indistinguishable from European civic monuments. For a city of 100,000, New York's Croton system was designed in the 1830s to supply 90 million gallons daily. The city's population in 1840 was 312,000. Daily consumption at that time, roughly 12 million gallons. The infrastructure was built for 7 times the existing demand. The standard explanation: visionary planning. Engineers anticipated growth and built accordingly. But the scale of overbuilding is consistent across dozens of cities. Boston, Philadelphia, Chicago, St. Louis, San Francisco. All installed infrastructure in the mid-1800s sized for populations they wouldn't reach until 1900 to 1920. Either every city had identical foresight, or the systems were inherited. The electrical grid shows the same pattern. By 1890, New York had multiple competing power systems: Edison's direct current, Westinghouse's alternating current. Within 10 years, the city had standardized AC distribution with grid capacity far exceeding demand. The first central power station, Edison's Pearl Street Station, opened in 1882 serving 59 customers. By 1900, Manhattan had 14 power plants generating enough electricity for a city 3 times its size. The cable conduits, transformer stations, and distribution panels were installed with systematization that implied central planning, yet no regulatory agency coordinated construction until after the grid existed. London's Underground, opened in 1863, used tunneling methods that wouldn't be formally documented until the 1900s. The Metropolitan Railway ran 4 miles underground with ventilation shafts, drainage systems, and station platforms built to dimensions still used today. The tunnels accommodated trains not yet designed. The electrical infrastructure anticipated electrification that didn't occur until 30 years later. Administrative records from the construction describe existing foundations and prior excavation in areas with no documented previous development. The Paris Metro, opened in 1900, followed a similar pattern. Its tunnels aligned with subsurface infrastructure, sewers, catacombs, crypts, with precision that suggested prior mapping. The system expanded rapidly, adding lines that seemed to follow pre-planned routes. In Chicago, the freight tunnel system built between 1899 and 1906 ran 40 miles beneath downtown streets at a depth of 40 feet. It connected every major building, handled coal delivery and mail, and used electric locomotives. The system required coordination among hundreds of property owners, utility companies, and city departments. Yet it was completed in 7 years with minimal disruption. The tunnels are still there, mostly forgotten. Flooded in 1992 when a construction crew breached the wall. Whether this reflects inheritance or convergent engineering solutions developed simultaneously across continents, the consistency creates friction. The timeline compresses. The labor requirements multiply. The technical precision appears before the educational institutions that should have trained the workforce. And beneath it all, one constant: structures sized for futures that seemed already known. The word Tartaria appears on European maps from the 15th through 19th centuries. It referred to the vast regions of Central Asia, Siberia, and parts of Eastern Europe, lands beyond immediate European control. The term derives from Tatar, the Turkic and Mongol peoples who inhabited these territories. Cartographers used it as a catch-all designation for areas they couldn't clearly define. It wasn't a unified empire. It wasn't a single civilization. It was geographic shorthand for the unknown. By the late 1800s, as Russian expansion and European colonization mapped these regions in detail, Tartaria disappeared from official use. The lands were reclassified: the Russian Empire, Qing China, the Ottoman sphere. The label became obsolete. In modern reinterpretation, Tartaria has been reconstructed as something else entirely: a proposed advanced civilization that existed globally before the 19th century, possessing architectural and engineering knowledge later obscured or erased from historical record. This interpretation draws on the architectural evidence we've examined: the exposition buildings, the infrastructure, the over-engineered systems. It suggests these weren't built by 19th century societies but were inherited, repurposed, or rebranded as new construction. There are 3 frameworks for interpreting the patterns. The first: conventional history is accurate, and what appears as anomaly reflects gaps in our understanding of 19th century capability. Rapid construction was possible through industrialization, prefabrication, and labor mobilization we underestimate. Over-engineered infrastructure resulted from optimistic planning and material abundance. The demolition of exposition buildings was economically rational. Temporary structures dismantled after serving their purpose. This framework accommodates the evidence within accepted chronology. It requires believing that Victorian-era engineers operated at the edge of theoretical knowledge, that labor forces worked with efficiency matching modern mechanization, and that hundreds of independent projects across continents arrived at nearly identical architectural solutions through parallel development. The second framework, the architectural and infrastructural record, suggests a predecessor civilization or advanced pre-industrial culture whose works were integrated into 19th century society. The exposition buildings weren't constructed, they were refurbished. The canal systems, aqueducts, and rail bridges weren't engineered from scratch. They followed existing templates or utilized surviving infrastructure. This interpretation explains the timeline compression, the technical precision, and the stylistic consistency. It accounts for overcapacity by suggesting systems were built for populations that once existed but had declined by the 1800s. It explains demolition as concealment, removing evidence of inherited origins to maintain a narrative of progressive development. This framework requires accepting that a catastrophic reduction in global population occurred sometime before the 19th century, that historical records were systematically altered or rewritten, and that architectural continuity exists beneath documented history. The third framework sits between the others, neither full acceptance of conventional chronology nor complete revision. It proposes that knowledge systems, technical manuals, or architectural traditions survived from earlier periods, perhaps Roman, Byzantine, or medieval, and were rediscovered or preserved through craft guilds, religious orders, or isolated communities. In this view, the 19th century didn't invent but rather recovered and scaled methods that had been practiced in fragmented form. The rapid construction wasn't anomalous. It represented the application of preserved knowledge to industrial resources. The classical architecture was an imitation but continuation of unbroken tradition. This framework allows for both historical accuracy and inheritance without requiring civilizational erasure. Let's return to 1816. The year without a summer. Volcanic eruptions in the East Indies ejected ash into the stratosphere, cooling global temperatures. Crops failed across Europe and North America. Famine followed. Populations migrated. Historical records describe widespread hardship. But they also describe something else: reconstruction. Within a decade, infrastructure projects began across the industrializing world. Canals, aqueducts, civic buildings. The timeline of development accelerated precisely after the crisis. If we follow the second framework, 1816 becomes a reset point, a moment when populations rebounded and repopulate spaces left empty. The infrastructure already existed, requiring only reactivation and expansion. If we follow the first framework, 1816 becomes a catalyst, an economic and social disruption that forced innovation and mobilized resources toward rapid rebuilding. If we follow the third framework, 1816 becomes a revelation, a crisis that exposed the fragility of contemporary systems and prompted rediscovery of more durable methods from the past. All three interpretations fit the same evidence. The framework you apply determines what you see. The metaphor of Tartaria isn't geographical, it's epistemological. It represents the space between what official records state and what physical evidence implies. Whether that space contains lost civilizations, forgotten knowledge, or simply underestimated human capability depends on which friction you find most compelling. The exposition buildings were demolished, but their foundations remain. The canals still carry water. The bridges still bear weight. The infrastructure still functions, outlasting its supposed temporary nature. The evidence invites examination beyond the binary of acceptance or rejection. It asks whether history is a single thread or a woven fabric with strands we've stopped tracing. The architectural record doesn't demand belief in Tartaria as a historical entity. It demands acknowledgement of the friction, the compressed timelines, the unexplained precision, the systematic overcapacity. Whether you attribute that friction to lost civilizations, recovered knowledge, or underestimated Victorian engineering is interpretive choice. But the friction exists. The buildings were built. The systems functioned. The timelines compressed. The labor materialized. The materials arrived. The engineering succeeded. And afterward, much of it was erased, not by conspiracy perhaps, but by progress. Cities grow over their own foundations. New infrastructure replaces old. The temporary becomes forgotten. What remains are photographs of buildings that shouldn't have been possible, maps of systems designed for futures that seemed already known, and mathematics that don't quite reconcile. The story of Tartaria in its modern form isn't about proving what was. It's about questioning what we assume must have been impossible. And in that questioning, the friction becomes something else. Not anomaly, but invitation. To look closer. To measure again. To ask what else might be standing in plain sight, labeled as something it isn't, waiting for someone to check the foundation. The evidence doesn't close. It opens.